All right, good afternoon, everyone. So I'm recording this Tuesday afternoon. It's Tuesday. You'll either see it later today or tomorrow, which is fine. Right? And we're going to be talking about, excuse me, we're going to be talking about spectroscopy. I've been having a hard time speaking today. I'm just a little tired, so I'm going to be mumbling some of my words. Oh, that's okay, though. So you watched, or you should have watched, the video on the 7 ages of starlight, right, which is really important. I'm going to talk about all the stages of star development, right? But to get all that information from the stars, to see what they are, how hot they are, what elements are in them, we need spectroscopy, right? We need this thing here. And you might have done some spectroscopy in high school chemistry. One sec, I gotta hit pause. Boop, 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 boop. Okay, sorry about that. Just had to speak with someone on staff. So, looking out into space, looking at the stars, light is how we get information of what's in those stars and how hot they are. Right? So, light is telling us all this information. The chemical composition, or what elements are found in a star, is determined by spectroscopy. Spectroscopy, spectra, the light, and scopy, using a scope. So a spectroscope analyzes the wavelengths of light coming in, right, and creates a spectrum. Right? So you should already be familiar with the electromagnetic spectrum starting in grade 10, right, where you've got your low energy to high energy. Low energy starting with the radio waves, microwaves, infrared, right, visible light being red, orange, yellow, green, blue, indigo, and violet, which combine to make white. Then ultraviolet, X-rays, and gamma rays going up in energy. Spectroscopy reads the light coming in. And we've got different scopes that look at different parts of the spectrum. We've got scopes that look at infrared. We got scopes that look for microwaves. We've got scopes that look for X-rays and gamma rays. Right? And then we just got our basic scopes, which look at visible light, right? Red, orange, yellow, green, blue, indigo, and violet, creating the continuous spectrum. So, first thing we need to discuss is that all matter gives off radiation, but nothing emits a perfect black body spectrum. And we'll talk about the black body in the second half of the notes for today. So don't worry about what the black body spectrum is right now. Right? That's going to be addressed in, so this is lecture 5A, that'll be in lecture 5B notes. So looking at radiation from space, right, and radiation includes white light, the light that we see, we can analyze it. We can analyze it using the spectroscope. Move me down there. So Kirchhoff's laws. A luminous solid or liquid, so something, a luminous meaning it's giving off light, or a sufficiently dense gas emits light of all wavelengths, and so produces a continuous spectrum of radiation, a continuous spectrum without gaps, okay, without gaps in it. A low density, where's my tool to mark this up? Sometimes it shows up, sometimes it doesn't. I'm not a big fan of this software. A low density hot gas, okay, emits light whose spectrum consists of a series of bright emission lines that are characteristic of the chemical composition of the gas. And 3, a cool thin gas absorbs certain wavelengths from a continuous spectrum, leaving dark absorption lines in their place. So what this means is, especially 1 and 3, right, you've got a hot star giving off a continuous spectrum. of radiation. That radiation travels through that star's cooler atmosphere, and that cooler atmosphere then absorbs some of that radiation, creating absorption lines. These absorption lines are specific to certain elements. Okay, elements have their own set absorption lines and emission lines. So here, from a light bulb or the body of a star, we should get the continuous spectrum of white light: red, orange, yellow, green, right, blue, indigo, and violet. If it was just a hot gas, like a hot cloud of gas out in space, you would see the emission lines. These emission lines are specific to different elements. Okay? Different elements will give off a different emission spectrum. But when the star is hidden behind a cold gas, or in this case, a cooler gas, right, the atmosphere surrounding the star, right, so the photosphere, the chromosphere, right, and the corona of a star, right, when the light from the core of the star travels through the cooler atmosphere, right, that atmosphere absorbs radiation. Right? These absorption lines, which we can see correspond to the emission line spectrum above, these absorbed lines tell us what elements are in the atmosphere of the star. So we can learn a bit about the elements. The star's composition and what elements are in its atmosphere. Just gotta hit pause. I got a student at the door. So, Lauren, when you watched that, that was me pausing it to talk to you about galaxies. Okay, let's continue on. Oh, wait, one more time. Let me just reinforce. Right? So, a star gives off a continuous spectrum of light. Right? The cooler atmosphere of the star is cool in comparison. It's still scorching hot. We would be vaporized if we entered it, but it's cool in comparison to the 15 million degrees at the core. But the cooler atmosphere of the star, right, the elements within it, they absorb some of that light energy, and it creates these lines. These lines are specific to different elements, so we can identify the elements within the atmosphere of a star based on the absorption line spectrum. We can look at the light given off by nebula. Nebula are clouds of gas, right? Based on the different spectrums they give off, we can we can determine. We look out into space and look at the Crab Nebula. Based on the absorption spectrum and the emission spectrum they give off, we can determine what are the elements in those celestial bodies. Okay, so the next thing I want to discuss, and I need you to just recall. I'm just going to sketch it super quickly here. Just give me a moment. The basic structure of an atom. So if you remember your Bohr-Rutherford diagrams, and hopefully you should from grade 10, just sketching it super quick. Okay, so we got the protons and neutrons in the center, and then in orbits around the atom, you've got the electrons, 2 in the first, 8 in the second, and so on. Those orbits are called energy levels as well, and they are at specific energies, right? The difference in energy between the first orbit and the second orbit is a very specific amount. And the difference in energy between the second and third, and the second and the third and fourth, and so on, are very specific amounts. They don't change. So let's read here. If an atom absorbs some energy in the form of radiation, so photons of light, whether it's visible light or X-rays or gamma rays or infrared, that energy causes internal changes. Similarly, if the atom emits energy, so if an atom or a piece of matter is glowing, imagine a piece of red hot iron. If you ever watched like Forged in Fire, and they're making knives, and the iron and the steel is red hot, and it's giving off light. Okay, so the matter or the atoms in that iron are giving off light. So similarly, if the atom emits energy, that energy must come from somewhere within the atom. Okay. The energy absorbed or emitted by an atom is associated with changes in the motion of the orbiting electrons. So the electrons are at energy levels. And you got the lowest level they're at, that's the ground state, that's where they're found naturally. And if I was to excite an atom, making it hot, let's say I heated it up in a forge, right? Heating up steel in a forge, the electrons are going to jump up to a higher energy level. But they're not stable there, right? They'll be there temporarily, then they'll fall back down. And when they fall back down, that energy they absorbed comes out. And if they fall back down, sorry, let me rephrase. So I heated them up, I gave them energy, they jumped up an energy level. Okay. Then they fall back down. When they fall back down, that energy they absorbed is given off, and it's given off as light. Okay, so some relevant points of the Bohr model of the atom. The ground state, or the lowest energy, that's the normal spot where the electrons should be, right? 2 in the first, 8 in the second, and so on. The unexcited atom has electrons at specific points. Number 2, there is a maximum energy that an electron can have and still be part of the atom. Once you give an electron too much energy, it dissociates from the atom and it leaves the atom. You now have created an ion. You now have an atom that's missing electrons. It is charged. Right? So we now have got these free electrons floating around, and we call that a plasma. And the third important point, electrons cannot exist between orbits or energy levels, right? They can only be found at the first, second, third, fourth, and so on, or given enough energy that they leave the atom completely. Next slide here. So electrons gain energy and, should we say, and can be excited and leave their ground state to orbit at a higher energy level. We call that the excited state. They can become excited by two ways: by absorbing some energy from a source of electromagnetic radiation. So absorbing radiation from someplace else, whether that radiation is from sitting out in the sun and the sunlight's hitting it, right? Whether it's being bombarded by X-rays from an X-ray machine, whether it's being bombarded by infrared radiation from a coal forge or a propane forge, right? All that heat, right? That's radiation. And electrons can be excited by atoms colliding together. Important to note here, point 2, an electron will not stay at the excited state. It can't stay there. It won't stay there. Within 10 to the negative 8 seconds, it will drop back down. So point 0.000008 or 0, okay, 0.000001 seconds, it will fall back down to its ground state. When it falls back down to its ground state, it will give off the exact same amount of energy it picked up. So the amount of energy absorbed or emitted corresponds precisely to the energy between two orbitals. Right? And atoms have specific electron orbits. If you remember hydrogen, it has one electron in the first orbit. Helium has two electrons in the first orbit. Lithium has two in the first, one in the second. Right? This is basic chemistry. You should know this. I'm not going to go back and explain it. If you don't understand that, oh, you're in trouble. Okay, moving forward. If you don't understand that, come talk to me. Or if you're not in the building, send me an email. So in this image, we're going to use hydrogen as an example. Okay, there's the nucleus of hydrogen. And I've got only a few minutes, so I got to pause and I got to teach a class. I got my grade 9s. So there's the nucleus of hydrogen. and there's its electron in ground state, right, in the first orbit. A photon of light, so some energy from light, strikes the electron, right? And it's got to be the precise amount, right? If it's not enough energy, it won't jump. It's got to be the precise amount, right? And it will jump to the next orbit, okay? But then it's not happy at the excited state. It's only going to stay there for that 10 to the negative 8 of a second, right? So it's going to fall back down, and as it falls back down, it emits a photon of light. It emits that radiation again as light. Okay? So if I'm heating up hydrogen gas, right, the electrons are going to be excited. They're going to jump up, and then they're going to fall back down, and they're going to give off light. So the gas is going to glow. So that can happen by running an electric current through a gas, heating it up, or sending radiation at it, other radiation to excite it. Okay, here, right, I've got hydrogen at the ground state, and let's say this photon that hits it is more energetic than the one above. It's got enough energy to push it up to the second orbit. Okay, so here it's pushing it to the second orbit, and then it falls back to ground state, giving off the energy that it absorbed. Or this part can happen, right? Where we've excited it to the second state, and then it falls back down to ground to the next orbit. It falls from the third to the second, right? And it gives off the energy from the third to the second, and then it falls back down to ground state, right, giving off a different energy of light. Right? So in this case, it's giving off different wavelengths of light. Right? So there's two possibilities, and both happen statistically 50% of the time. Right? So in this case, right, considering both together, because both happen 50% of the time, there's going to be three different wavelengths of light that could potentially be given off. Dropping from the third to the first, or dropping from the third to the second, or dropping from the second to the first. Those are all the potential wavelengths. Okay? So hydrogen gas, if we look at the emission spectrum, there's multiple lines in its emission or absorption spectrum. Okay, and I'm going to pause that and fix this because this is going over my text. Just give me a moment. Hit pause. Actually, I'm going to have to hit pause. I'm going to have they're going to be here in about 3 minutes for my grade 9s. So I'll teach my grade 9 class, and then I'll come back at the end of the day. So I'll be done with them about 2:30. 2:30, I'll finish this lecture here on spectroscopy. Okay, sorry about that. Let's continue this. Not 100% sure where I left off. Swap that. Move me. Let's go over here. And let's go this way. Okay. And maybe here again. Who knows? So back to here. And I just saw a spelling mistake. That's not how you spell occur. So we've got an atom of hydrogen, photon of light, so radiation strikes the electron. And if that amount of radiation that energy is the same as the energy to jump from the first orbit to the second, the electron gets excited. Then it falls back and it emits that same amount of radiation. So that would be a specific wavelength of light. Okay, it's always specific amounts. Right? If a photon of light hits, right, with say a little more energy than the second orbit, it can't go past the second orbit. You need to have the correct amount of energy to go from first to second, from second to third, and so on. This example here, photon of light hits the hydrogen atom, excites the electron, but it had enough energy to jump 2 orbits. When it falls back down to ground state, it can do that in 2 ways. It can fall all the way back, emitting the same wavelength of light that struck it to make it jump 2. Or when it falls back down, it can fall back down from the third to the second and emit that much energy, so one particular wavelength, and then it can fall back down from the second to the first and emit another photon of light. So it can emit 2 different wavelengths of light. And both of these situations, this situation and this situation, happen roughly equally, 50%, 50%. Okay, continue. So this is me here explaining what's happening. So from the previous image, we can see that there are multiple ways an electron can return to ground state. It can fall all the way back down, emitting all the energy absorbed in one blast, or it can cascade one orbital at a time, emitting different wavelengths of energies, right? And these energies correspond to the difference between each orbit, between each energy level. And it emits several photons of light. And either possibility can occur, or as I like to say, occur, right? That's not incorrect at all. Don't listen to me. Either possibility can occur with a roughly equal probability, so 50%, 50%. So, in a sample of heated hydrogen gas at any instant, atomic collisions ensure that atoms are found in many different excited states. Okay, so you're going to get some where they're excited 1 step, 2 steps, multiple steps. The complete emission spectrum, right? So here's the emission spectrum, therefore consists of wavelengths of possible transitions between those states and lower states of energy. So this emission spectrum shows all the energies that can be emitted from a hydrogen atom. From being excited to the first to the from the first to the second, or from the first to the third, it shows all the possible combinations of electrons falling back down. So hydrogen will give off this emission spectrum. A cloud of cool hydrogen gas, though, on the other hand, if light is coming through it, right, and that radiation is traveling through a cloud of cool hydrogen gas, right, that radiation is going to excite electrons in that cool cloud, right, and that cool cloud is going to absorb those energies at the same energies that it would emit, right? So it's going to absorb those energies of light, and it's going to excite electrons in the hydrogen, and we get the absorption spectrum. Note that it is the exact same as the emission spectrum. So hydrogen is hit, electrons get excited, they fall back down, and they emit these wavelengths of light for hydrogen. A cloud of cool hydrogen gas, right, is struck by a continuous spectrum of radiation from a star. So the atmosphere of a star is struck by the radiation of that star from its core. Right? The hydrogen gas in the atmosphere is going to absorb those energy levels so that electrons can get excited. And in absorbing those energy levels, we see these missing bands that correspond to exactly what would be emitted. Hey, if that doesn't make sense to you, please send me an email and we can arrange a meeting to talk a little more. Right? Make sure you watch the YouTube videos as well. So this here is just this diagram enlarged, the continuous spectrum of the star, what heated hydrogen gas would give off, right? And this is what a cool cloud of hydrogen gas would do when radiation passes through it. It absorbs the same energies. This spectrum is specific to hydrogen alone. Sorry about that. A teacher just walked in the room, needed to discuss a student. Okay. So, yeah, you probably didn't see the pause. I just hit pause and it probably just, yeah, whatever. Moving forward. So, inside a star, okay, a hot, dense object, like a star, will emit a continuous spectrum through a relatively cool, relative to the core of the star, still super hot, low density gas, the star's atmosphere. This results in absorption lines that correspond to the emission spectrum of the gas cloud or the atmosphere of the star. Only the photons with precise energy to excite electrons in the star's hydrogen atmosphere will be absorbed. The rest will pass through, creating the absorption spectrum of a star. So only the photons that have that specific energy to jump it from one orbit to the next, or from one orbit to the second, or from one orbit to the third, right? Only the specific energies will be absorbed. If an electron has, 1.5, right, it will pass. Sorry, if a photon has, 1.5 energy, it will pass through and come out and reach our eyes. In very hot stars, the ionization of an atom, so an atom it's so hot that the electrons get removed from the atom. So the removal of electrons alters an atom's structure, and the energy levels of an ionized atom are very different from those of a neutral atom. Each level of new ionization introduces new possibilities of spectral lines. Okay? So ionized atoms, ionized hydrogen will give you some more lines so that we still get that unique absorption spectrum for our gases. So when we look at a star, right, you're going to see the lines for hydrogen. Then you might see the lines for helium, right, all blended together, like in that video you watched. You should have watched it yesterday, or probably today. Yeah, never mind. Yesterday, because you're going to be watching this tomorrow. Anyways, so you look at a star, and you can look at the lines in the spectrum, and from that you can say what is the elemental composition of the atmosphere of that star, right? So this is how we learn what makes up objects in space, right? We look at their light, and from their light we can infer a lot of things. Okay, I'm going to stop there. So tomorrow, tomorrow I'll be posting your test. Okay, I'll talk about that a little more when I post that tomorrow afternoon. It's going to be pretty straightforward. I do want to mention this now. Okay, your test uh, is to be. How am I going to phrase this? Like, your test is to be handwritten and scanned, not with a picture. Your answers are to be handwritten and scanned. So like you're printing it on paper and you're scanning it so I can read it. Okay? So that's to avoid people cutting and pasting. Second, use the material you've learned from me. Okay? Don't start adding extra material that goes a lot deeper into it. Right? You're just going to confuse yourself. I'm trying to keep things as simple and straightforward as possible. If you want to do extra research, great, but I'm looking for what we talk about in this class. Okay. Third, if the level of writing that I see is beyond what most grade 12 students can do, it's going to trigger me, right? It's going to trigger my brain and say, that sounds kind of funky, right? And I am going to, I'm just going to, take that sentence or that paragraph, put it into Google, and it will find me where it came from. Okay. So actually, the handwritten thing we're going to scrap. You can type it if you want. I prefer handwritten for tests, but typing is fine. If the text does not look like, if it's at another level of writing that I wouldn't see from a grade 12, I'm going to check. Okay. And I just love catching people cheating. Right. It just makes me smile. All right. Enjoy.